Hello students, it's Professor Sansom. Today we're going to be talking about doing titrations with weak acids or bases. And like the regular titrations with strong acids and bases that we talked about last time, this time we're going to be concerned with 4 different points during the titration. So when we have just the initial solution all by itself in water, when we're between the beginning and the equivalence point. For a weak acid, that's called the buffer zone. And then at the equivalence point, when we have the conjugate base of the weak acid that's left over. And then finally, after the equivalence point, when we've added excess base. And so we'll be looking at these different points in the titration. Before we do that, we have a quick Podia quiz. This is just to make sure that you guys learned what you were supposed to learn last time. So supposing you're titrating 50 milliliters of 0.2 molar nitric acid with 0.1 molar KOH, what is the pH after adding 25 milliliters of KOH? I'll give you guys 3 minutes to go ahead and do this. And Tia, you can go ahead and pause the video. Okay, so if you did a BCA table, you would see that all the hydroxide ion gets used up and we have excess acid. So this is actually before the equivalence point. We have 0.0075 moles of acid in 0.075 liters, which makes our H plus concentration 0.1, and that makes our pH 1. So the correct answer here is A. So today we're going to talk about the weak acid strong base titration, and it looks a lot like the titration curve is going to look a lot like the strong acid strong base titration, but there's a few things that are different. So first, at the very beginning, the pH is usually lower if it's a strong acid. It might be about pH 1, but for a weak acid it'll be higher. That's because it's not fully dissociated. So at the beginning we have our weak acid in water, which means that our Ka equilibrium is going to be controlling the concentration of hydrogen ions and the pH. And then as we continue on this titration curve, you can see it has this kind of curvy shape and then it's sort of flat in the middle before it goes up at the equivalence point. So this zone here in the middle is often called the buffer zone. And that's because when you have a weak acid and you react it with a strong base, the thing that you get on the other side is the conjugate base of the weak acid. And so here in the middle, we're going to have a mixture of the weak acid that's not yet neutralized and the conjugate base that's formed when it reacts with base. And then finally, I don't know why my mouse keeps going away. Here we have the equivalence point where, again, it's a steep change in the pH from acidic to basic. And at the equivalence point, you'll notice, even though our acid is completely neutralized, our pH is not 7, it'll be greater than 7. And that's because at the equivalence point, what's remaining is our conjugate base. And so the conjugate base is going to be reacting with water, and we'll have just the Kb equilibrium to consider here. After the equivalence point, it goes up sharply and eventually it'll just be the pH of the base that we're adding because we'll have excess base, no more acid around, and so we'll just calculate the pOH from the concentration of our base. In order to look at this weak acid strong base titration, we'll want an indicator that changes color near 7 plus 1/2 of the pKa, which is sort of just an approximation, basically to say a little bit higher than 7. Okay, so there are 4 points in the titration that we're going to be concerned with. This is the same as for the strong acid titration. We'll have an initial solution of weak acid. The only thing that's different here, remember, our weak acids have equilibria that we have to consider. The strong acid that we did last time, we just had to take the negative log of the hydrogen ion concentration. Because this is a weak acid, we'll first have to find the concentration of hydrogen ions using the Ka and a Rice table. And then we can take the negative log of the hydrogen ion concentration to get the pH. So the major thing that you have to remember this time using a weak acid, strong base titration is that every time you have a weak acid or a weak base, you're going to have to use some kind of equilibrium situation, like a Rice table or the Henderson-Hasselbalch equation, something to deal with that equilibrium. Last time it was easier because we only had to deal with the strong acid or strong base. Okay, so at the very beginning, we'll just have our Ka equilibrium with our acid and water. Then we have the buffer zone that happens before the equivalence point. If we're in that area of the titration, we'll do a BCA table using moles to find the moles of acid and then the moles of conjugate base that are produced when it's neutralized. And then, because we have a mixture of the acid and its conjugate base, we'll use the Henderson-Hasselbalch equation. At the equivalence point, we'll have just the conjugate base of the acid remaining, and so you'll use a Rice table. Make sure you use the concentration with the new volume of the conjugate base, and you'll use Kb, which you'll calculate from the Ka. So again, remember, as you're doing this titration, as you go along, the volume of solution is changing. So make sure that you account for that at each point in the titration. Finally, we have after the equivalence point, we'll use a BCA table to find the moles of excess base. And now this one is easy because we have a strong base that's around, so we'll just do a pH calculation with that strong base with the hydroxide concentration. And because it's stronger than the weak base, we don't have to worry about the weak base contributing to the pH at that point. Okay, we have another Podia quiz, and this will be the first step in what we're going to do with our practice problem here. So for the titration of 80 milliliters of 0.1 molar formic acid with 0.2 molar NaOH, what volume of NaOH must be added to reach the equivalence point? So take a couple minutes to work on this. This is exactly the same kind of math that you did before. This is, by the way, a monoprotic acid. It's just this proton here that's acidic. So monoprotic acid and monobasic base. TA, you can go ahead and pause the video for a second while people work on this. Okay, so we should have gotten 40 milliliters as the volume of NaOH that's added to reach the equivalence point. That makes sense because we had 80 milliliters of 0.1 molar acid. Our base is 0.2 molar, so we should need half as much of that solution in order to get to the equivalence point. So now again, this is going to be useful because when we're doing this problem, every time we do a titration, we want to start with when is the equivalence point going to happen. That's really useful so that we know which strategy we have to use. If we're before the equivalence point, at the beginning, at the equivalence point, or after the equivalence point. Okay, so here's our practice problem, and we already did the first part. We calculated it would be 40 milliliters to reach the equivalence point. Now there are parts B, C, D, E, and F here, which are going to be for different points in the titration. We have the Ka for formic acid. So what I'm going to ask you guys to do is to work on each of these problems, and in between, Chelsea will help you solve the problems, show you how to do it, and check your answers here. So go ahead and work on part B, and you can go ahead and pause the video here to do part B. Okay, so you should have completed part B, and the initial pH is just using the Ka calculation for our formic acid, and you should have gotten 2.38 using your Ka table. Now go ahead and work on part C. What is the pH after adding 20 milliliters of NaOH? Notice that 20 milliliters is half of 40 milliliters, which is when the equivalence point is. So this is the pH at the half equivalence point. Go ahead and pause the video again and take a minute to do that. Okay. Hopefully you guys got 3.75, and this is just the pKa because at the half equivalence point, the pH equals the pKa. So 3.75 is the answer there. Now, part D is the pH after adding 35 milliliters of NaOH. This is still before the equivalence point, so you're going to need to use a BCA table to figure out how much of your acid is left and how much of the conjugate base has been formed. And then you'll use a Henderson-Hasselbalch equation to find the pH. So go ahead and pause the video again. And hopefully you guys came up with 4.59. So the pH is starting to get higher as we're getting closer to the equivalence point. Part E, what's the pH at the equivalence point? So now you will have added 40 milliliters of your NaOH, and you will have completely neutralized your formic acid. So at this point, you can do a BCA table and then get the concentration of the conjugate base. Remember, there's a new volume. When you have the concentration of the conjugate base, then you'll do a Rice table to find the concentration of hydroxide produced by that conjugate base reacting with water. So go ahead and pause the video again here and do that part. So hopefully you guys came up with 8.28. As expected, the pH is higher than 7, and it's at about 7 plus about half of the pKa. The pKa is 3.75, so like this is about 1 1/4 above 7, so we expect it to be in that range. Okay. What is the pH after adding 60 milliliters of NaOH? This is the last part of the question. This is going to be after the equivalence point. You'll do a BCA table and then just calculate the concentration of OH minus to get your POH and pH. Go ahead and pause the video and do that calculation. Okay. Hopefully we came up with 12.46 for that one. So this is a practice problem that you can always review again, and also there is a practice, there's a video on YouTube that you can watch showing a weak acid titration for a different problem that'll go through all of these same steps again. So if you feel confused about doing this and you want to see another worked example, go ahead and watch that video. Okay. Couple last things that I want to talk about. So one thing is polyprotic acids. Polyprotic acids end up having multiple equivalence points, and you do the calculations just the same way that you would for the weak acid that we've talked about, except you just have to think about which Ka is it that you're looking for. So, for example, if you have a triprotic acid, when you're to the half equivalence point for the first one, you'd use the Henderson-Hasselbalch equation, but your pKa would be for Ka1. And if you were here, you would use your pKa2 for that half equivalence point. And likewise, at the equivalence points, you're going to make sure that you're using the appropriate Kb for the base, the conjugate base reacting with water. We can also have a weak base, strong acid titration. It's just like what we did before. We use the same 4 points at the beginning, before the equivalence point, at the equivalence point, and then after the equivalence point. It operates in the same way. The only things that are going to be different are that at the beginning you'll use Kb. At the equivalence point, you would use pKa for the conjugate acid of the weak base. And then at the end, you would expect, of course, your pH to be acidic because you'll have excess acid that you've added. So to summarize at the end here, go ahead and answer these questions. What's the procedure if you have a weak acid only, if you have a weak base only, if you have a mixture of acid and base when at least one of them is strong, and then if you have a mixture of a weak acid and its conjugate base? You're going to do something different to find the pH in each case. Thanks for listening today, and have a great day, you guys. See you soon.